Hello, welcome to the Lamont-Doherty Core Repository. My name is Nichole Anest. I am the curator of this facility, and I will be your virtual tour guide today. As a note, all of the maps and images, posters, most of the items in the lab, images of all of them with detailed information will be available online as a supplement to this virtual tour. Thank you, and I hope you enjoy it. Here is a map of the collection at the Lamont-Doherty Core Repository. We have just over 20,000 samples in our collection. The different colored dots on this map represent the ships that collected the various samples. Our first two ships, the Vima and the Conrad, in operation for just over 30 years collectively, were under the jurisdiction of our founder, Dr. Maurice Ewing. He told the captains of those ships that no matter where they were, no matter what else they were doing, they had to stop and take at least one core every day. So that is why you can see these ships' tracks plotted out across the oceans. The closer the sample dots are, the slower the ships were moving. So what were they looking at there? What were they looking at here? Well, you can see on the map how the blue is paler. So those are actually the mid-ocean ridges. So the ships were studying the mid-ocean ridges, and in conjunction with that, they were taking sediment cores. So what is a sediment core, and how do we get them, and how do we use all of this mud? Well, here's a model of a sediment corer, right? A piston corer it's called. The pipe here represents 20 feet, and this can be up to 1 ton of weight, the core head. The amount of weight you put on there depends on the type of sediment you think you need to penetrate. The core barrel that's in operation today is 140 feet long. It can be up to 160 feet. So a piston corer is lowered from the side of a ship, plunges into the mud at the bottom of the ocean, and then gets pulled back up to the ship. The mud is laid down with the oldest sediment at the bottom and the newest sediment on top. So the deeper we can go, the longer our coring barrel, the further back in time we can go in the mud at the bottom of the ocean. And how do we use that mud? How do we determine how old it is? What Earth's climate history was like? All of that. So here are images of different types of plankton shells. So some species of plankton build shells. They're single-celled organisms. And while they're alive and building their shells, they're incorporating the chemistry of the seawater into their shells. That chemistry changes with Earth's climate. So we can use these sand-sized grains, these plankton shells, to determine what Earth's climate was like going back millions of years. So we're going to move into the main lab now, and then I will show you some more mud. So here we are entering the main lab area of the repository. We'll come back out here in a moment. But first I want to show you one of our storage lockers. This is the Vima storage locker. So all the cores in here were taken on our first ship, the Vima. They are all stored in these metal trays. They are labeled with V for Vima, and then the cruise number, core number of that cruise, and the length of the core in the tray. These trays are 8 feet long. So a core comes up, it's cut into, in this case, 8-foot sections, and then each section is split in half down the middle lengthwise. So we would have B for working halves and A for archive halves. So we sample the working halves first, but we do occasionally dip into the archive halves if it's a quote-unquote popular core. if it has a lot of good data to tell us. The mud in all of these trays is dry because when we were getting the cores back, a core a day, right, very quickly, very rapidly, they didn't actually know what to do with all of the mud, so it was allowed to dry out. Now, however, we refrigerate everything and try and keep it wet as long as possible. Here are a couple of examples of different types of mud, and we'll look at some more of those examples in a moment. Here we have several different types of mud. You can see that they are all a little different. Some are made up entirely of microfossils. This one from off the coast of the Yucatan Peninsula, the one on the left, is made up entirely of shells of different types of plankton. The one next to it is off the coast of Indonesia, and it has all these pumice bombs in it. If we go over here, we can see a core. This is styrofoam, where the core has been sampled, and then we put styrofoam in to just maintain the stratigraphy of the core. This core was taken in the Eastern Mediterranean, and this band right here, this gray band, is ash from the Vesuvius eruption that buried Pompeii. So depending on where the core is taken, it can tell us a lot about historical events, archaeological finds, things besides Earth's climate history. Here we have a series of annual bands of diatoms. So diatoms are a type of plankton. They're actually an algae. They bloom in the spring and die off in the winter. So we have annual bands of their shells raining to the sea floor, going back to the last ice age, where the mud is just uniformly gray. Lastly, on this table of cores, I want to talk about these two. This is the bottom. I'm going to work my way to the top. They tell vastly different stories, but not just that, they show you how different sedimentation rates can be. So each of those trays is 8 feet long. They're the same length. But the one on the right, with the pile of rocks and debris at the bottom, is an underwater landslide called a turbidite. This one was laid down in a matter of hours to days as the finer stuff at the top settled out of the water. The core next to it, however, the bottom here, is 120 million years old. Same amount of material, vastly different ages. This core here tells a story of sea level change. So originally, it's very black mud, so that means it's organic rich. So it had to be very close to a continental shelf near the shore of a continent. It's the only way to get that much organic debris into the ocean. Then something happened. We presume sea level rose, washed away some of the organic matter, and then we have chalk being deposited. Chalk is plankton shells. This means that the water was deep enough for the plankton to live there, but then the color keeps changing, and it gets more tan instead of white. This, to us, says that sea level kept rising. So below roughly 3,000 meters in the oceans, that's an average, calcium carbonate gets dissolved because of all the pressure on top of it. So as water sea level rises and the water gets deeper, all of the carbonate shells, all of that chalk gets dissolved. So you only have this tan aeolian, so wind-blown muds. Then sea level drops again, and we have chalk resuming. Here are a couple of posters. These are available online as well. The one on the right is talking about the ice ages. So here we have a climate record going back 5.5 million years. Present day is on the right in this graph. Why does Earth's climate change naturally and very cyclically? Well, it's due to what are called Milankovitch cycles. And those are our orbital cycles around the sun. We have our eccentricity, right, where Earth's orbit goes from being very elliptical to slightly more circular. We're tilted, right? So our axis of rotation is not straight up and down relative to our plane of revolution around the sun. And we wobble like a top. We don't spin on our axis cleanly, but there is a bit of a wobble there. Combined, these three cycles give us currently a 100,000 year ice age cycle. And that's what these up and down wiggles mean, right? Right now, our temperature is way off the top of the graph there. But all of this data, the wiggles on the graph, the temperature change, we get both from the ice core, right? So that's what Vostok delta T means. Vostok, it was an ice core. But forams, foraminifera, different types of forams. We can tell what Earth's climate was like going back millions of years based on the chemistry of their shells. So we know that Earth's climate history has changed dramatically, both hot and cold, going back millions of years. This poster is showing us a core that was taken about 200 miles east of Florida, and it has remnants of the asteroid impact 65 million years ago. So that, as it says, is the moment of impact. All of the greenish debris was ejecta from the asteroid's impact into the Gulf of Mexico. It's all molten rock, which cools into little spherules as it flies through the air. So all of this debris, all of this ejecta was thrown into the atmosphere and then rained back down gradually over days to weeks, depending on how fine it was. Before the impact, foraminifera were more ornate and they were larger than they are today. The impact didn't just help kill off the dinosaurs, but it killed off most of the ocean's life, especially the smaller plankton. And they didn't return until several years after the impact. And when they did, they were much smaller and plainer than beforehand. Here we have an image of some of those spherules through the microscope. Here is a rack of unsplit cores from the Hudson River. They are in clear plastic liners. And this one in particular shows a distinct change in the mud from brown to black. The brown mud is clean mud, quote unquote. The black mud is undecayed organic matter that was left behind when all of the bottom feeders were killed off by pollution. So undecayed organic matter, mostly plant matter, that has lain on the bottom of the river forms a sapropel. We see these in other cores, most notably in the Eastern Mediterranean. In the Eastern Mediterranean, however, they are not caused by pollution, but by excess rainfall over what is now the Sahara Desert. And I will talk about that in a little while. Here we have a wet core. This one is wrapped in saran wrap to help keep it wet. It was taken in the Eastern Mediterranean. This is the top. And then we come down section by section. You can see the color changes. This, where there's a big jumble of clays, this is another underwater landslide. Now we get back to these black layers here. And then even more at the bottom. They are the same as this very large one near the top. And they are called sapropels. A sapropel is a layer of undecayed organic matter. So Mediterranean Sea, right? It's enclosed by land. A lot of plant debris gets washed into the Mediterranean every year. In this case, that organic matter was not broken down by bottom feeders. So when you have undecayed organic matter accumulating at the bottom of a water basin, and then being entombed by clay on top of it and being preserved that way, it's called a sapropel. The Mediterranean has these sapropels all over the eastern half, and they are caused indirectly by our orbital cycles around the sun. So roughly every 20,000 years, there is rain where there is now the Sahara Desert. So roughly every 20,000 years, the rain belt that is south of the Sahara moves north. And there's so much freshwater input into the Mediterranean from the Nile that it acts as a lid on the Mediterranean and causes the waters to stagnate. When that happens, all the critters that live in the sea and on the bottom of the sea die off because there's no more oxygen left. And because there are no more bottom feeders, all of this organic matter builds up and just sits there and forms sapropels. So all throughout the Eastern Mediterranean, we have this climate record of roughly every 20,000 years, large rain events over the Sahara. So we don't only have sediment cores here, but we also do dredging. So that's when you drop a chain basket off the side of a ship and drag it along the ocean floor. Sometimes you get giant rocks like these that are basalt flows, so lava flows from mid-ocean ridges, like that one and this one. This one here, you can see the different layers as lava was flowing out of and cooling out of the mid-ocean ridges. But mostly, or a lot of the times, we get manganese nodules. That's what these all are. They look different. They are different sizes. But they all start out the same. You can see on this one that there was something in the middle, most likely a shark's tooth, that acted as a nucleus. And due to bacterial action on the surface of that shark's tooth, metals started being precipitated out in rings. So manganese nodules are actually rocks that grow over time. They grow at an astonishingly slow rate. Here are some where you can see shark's teeth poking out of them. Here are some that are super tiny. But certain areas, I'm not sure how well you'll be able to see this, but wherever it's red on this map, the sea floor looks like this image. Literally covered in manganese nodules. As I mentioned, we now keep all of our cores refrigerated and wet as long as possible. So they're stored now in these deep tubes, so plastic tubes, and the cores live inside of them. We have an area where we just expanded to, so that's why we have all these empty shelves. The temperature in here is kept at about 40 degrees Fahrenheit. So it's just like stepping into your refrigerator at home. This core is from the North Atlantic. And it was one of the first cores to give us a very high resolution record of temperature change in the North Atlantic. This core was situated right here, so west of the British Isles, but way up there in the North Atlantic. It is actually quite a high sedimentation rate area, so they were able to get 1,000-year resolution from this core. Each of these little gouges in the mud, right, is where they took a sample. But this core, I'm not sure how well this will come across on the video, but you can actually see slight color changes just with the naked eye. It's much lighter, and then it'll get slightly darker, right? So it's varying shades of off-white to tan. Where it's lighter, that's an interglacial, or a period of time like today. So an in-between the glacial cycles. So it's mostly forams being laid down, so it's whitish, it's chalkier. Whenever we get to a glacial period, like down here, the color of the mud gets a little bit darker. And that's because as the glaciers are coming off of land, they've scraped up a lot of rock and debris, and so they're dumping all this ice-rafted debris into the oceans. And that's why the mud gets darker. This core, we've also, because it had such a high resolution to it, and we knew the dating of the layers very well, we were able to put historical time markers on it. So you can see, as an exercise in deep time, let's say, the very top of the core, it was collected in 1979. But then as you pan down, you'll be able to see, right, the fall of Rome happened in just the top 10 centimeters of this core. Most of it has been sampled away, but because we have these orange tags, we know where we are. But yeah, so you can see that as far as mud at the bottom of the ocean is concerned, all of our impacts on the planet have been sequestered in the top 10 centimeters of the mud. So I hope you've enjoyed this tour of the repository, and when things get back to normal, I hope you can come and visit us. Thank you very much.